If you trace your family tree back far enough, past every grandparent, past anything with a face, you eventually reach ancestors who survived a planet trying to freeze itself to death. Not an ice age, not a cold snap. Ice, possibly reaching from both poles almost to the equator more than once. Whole ecosystems your evolutionary line depended on disappeared under it for tens of millions of years at a stretch. And somehow, something got through, because you're here. Here's how a planet does this to itself, and how anything walks away from it alive. It starts with a feedback loop so simple it's almost embarrassing. Ice is bright. It bounces sunlight back into space instead of absorbing it. So if ice spreads even slightly, the planet reflects a little more heat away and cools a little more. A little more cold makes a little more ice. More ice reflects more heat. The planet cools again. Run that loop far enough, and it stops needing a reason. It just needs momentum. In 1969, a Soviet climatologist named Mikhail Budiko built a simple model of this and found something that should have alarmed him. Once ice spread past a critical latitude, somewhere close to 30 degrees, by later estimates, the feedback stopped behaving gently and started running away on its own. His own equation said the planet could lock into permanent ice with no built-in way back out. So Budiko looked at his own result and decided it must never have actually happened, because nothing in his math showed an exit. He was right about the physics. He was wrong about the history. 5 years earlier, in 1964, a British geologist named Brian Harland had already dug up something that made no sense by itself. Glacial debris sitting in rock that had formed near the tropics. Glaciers don't reach the equator, not in any climate regime anyone understood at the time. Unless, at some point, they had. The idea sat half-ignored for close to 30 years, filed under interesting, probably an error. In 1992, a Caltech geobiologist named Joseph Kirschvink gave the hypothesis a name that finally stuck, Snowball Earth. 6 years later, Paul Hoffman and Daniel Schrag went looking for confirmation in the rocks of Namibia, and found something specific, thick beds of limestone sitting directly on top of glacial debris, laid down fast, right as the ice was collapsing. That layering is the signature of a climate flipping from deep freeze to greenhouse heat almost overnight, geologically speaking. That's the kind of evidence that turns a fringe idea into a mainstream theory inside a decade. So sometime between roughly 720 and 635 million years ago, in a stretch called the Cryogenian, it looks like Earth did this twice. The first freeze, the Sturtian glaciation, lasted around 57 million years. Long enough for entire evolutionary experiments to rise, fail, and never get tried again. The second, the Marinoan, was shorter, somewhere around 10 to 15 million years, but hit many of the same latitudes just as hard. Picture what that actually does to a planet whose life runs almost entirely on sunlight. Oceans locked under kilometers of ice. Light unable to reach the water most organisms depended on for food. Rain slows or stops across huge regions because frozen ocean doesn't evaporate the way open water does. Nutrients that normally wash off land into the sea simply stop moving. On paper, this should have been close to a full reset button for life on Earth. It wasn't. And the reason it wasn't is the interesting part. Not every patch of that ocean froze the same way, and even where it did, frozen doesn't automatically mean sealed. Sea ice, even today, isn't one uniform block. It's threaded with narrow channels of leftover brine, water too salty to freeze at the same temperature as the ice around it. Those channels are cramped and chemically brutal by any normal standard. Microbes live in them anyway. Around modern Antarctica, cracks and thin patches in sea ice can be dense with microscopic algae, using whatever light manages to get through. If anything similar existed during the Cryogenian, it wouldn't have needed the whole ocean to stay open. It would have needed a crack. On top of the ice, a different kind of shelter could form. Meltwater pools, fed by sunlight strong enough to reach the surface near the equator. Shallow, salty, fully exposed. Not exactly comfortable. But to a single-celled organism, a puddle can be an entire ecosystem. Modern Antarctic meltwater ponds are packed with microbial life today, which is a large part of why researchers take the ancient version of this idea seriously. Then there's the shelter that never needed the sun at all. In February 1977, scientists piloting the submersible Alvin found something near the Galapagos Rift that broke a rule biology had assumed was universal, a whole ecosystem living around scalding cracks in the deep ocean floor, running on chemistry instead of sunlight. Hydrothermal vents don't care what the sky is doing. They're powered by heat and dissolved minerals leaking up from inside the planet itself. During a snowball Earth, the surface may have gone dark and nearly dead. The seafloor underneath it never got the memo. Bacteria near those vents could keep converting raw chemical energy into food, in total darkness, under a sky-sized lid of ice, indifferent to whatever the sun was or wasn't doing 4 kilometers above them. None of these refuges were generous. Cracks, brine channels, shallow puddles, and vent chemistry are marginal real estate at best. But survival never required the whole planet to stay livable. It only required enough scattered pockets for at least one lineage to keep a pulse. That's most likely what happened. Not one heroic sanctuary, but thousands of small, forgettable ones, each irrelevant on its own, together enough to matter completely. Not everyone agrees it got that extreme. Some researchers argue for a slushball Earth instead, a thin band of open water surviving near the equator the whole time. No total seal, no cracks required. The rock record hasn't fully settled the argument. Either way, whatever survived eventually had to get out from under the ice, and the way out is almost as strange as the freeze itself. Volcanoes never stopped, even under a fully frozen surface. Normally, the CO2 volcanoes release gets scrubbed back out of the atmosphere by rain and rock weathering, water reacting with exposed stone and pulling carbon back down over time. Under a snowball Earth, most of the exposed rock sits buried under ice. Weathering nearly stops, so the CO2 just kept accumulating year after year for millions of years with almost nothing pulling it back out. Eventually, greenhouse heat built up faster than the ice could reflect it away, and the feedback loop that had spent millions of years running toward cold started running the other direction. Once bare rock and dark ocean started showing through, they absorbed the sunlight ice used to bounce away, which melted more ice, which exposed more dark surface. The same runaway math that froze the planet unfroze it just as fast. The cap carbonates Hoffman and Schrög found in Namibia are the fossil record of that flip, the geological hangover of an atmosphere suddenly dumping a stockpiled overdose of heat and carbon into a thawing ocean. What came out the other side wasn't the planet that went in. Glaciers had spent tens of millions of years grinding raw minerals off continents, and all of it washed into oceans that were suddenly ice-free and starved for nutrients no more. Oxygen levels shifted. Ocean chemistry reset. Ecological niches that hadn't existed before suddenly did. Not long after the Marinoan glaciation ended, the fossil record starts filling with something new. The Ediacaran biota, among the earliest complex multicellular organisms found anywhere on Earth. Not much later, in evolutionary terms, comes the Cambrian explosion, the stretch where most modern animal body plans show up in the fossil record within a geological blink. Nobody serious claims the ice directly built animals, like flipping a switch. Evolution doesn't work that cleanly, and the exact chain of cause and effect is still argued over. But the timing is hard to wave away. A planet gets stress-tested down to its last scattered refuges, gets chemically rebuilt from the ground up, and shortly afterward, complexity takes off like it had been waiting for room to grow. This also isn't the first time Earth pulled something like this. A much older, even longer freeze, the Huronian glaciation, may have done something similar over 2 billion years earlier, right around the time oxygen first flooded the atmosphere. Snowball Earth, in other words, might not be a freak accident. It might be one of the planet's recurring settings, and it's become more than ancient history. It's a working model for people looking for life somewhere other than Earth. Jupiter's moon Europa and Saturn's moon Enceladus are both wrapped in kilometers of ice, sitting on top of oceans that have likely stayed liquid for billions of years, kept warm from below by tidal flexing instead of sunlight that's too far away to help. If life can run on vent chemistry under a frozen ocean here, on a planet that briefly looked exactly like that, there's no obvious reason the same trick couldn't be running under the ice somewhere else right now. Every mission being designed to drill, melt, or sample through that ice is, in a real sense, testing a hypothesis first written into Earth's own rock hundreds of millions of years ago. Every plant, animal, and fungus alive today is one unbroken thread running back through those cracks in the ice. Not through one lucky survivor in one perfect shelter, but through thousands of tiny, marginal, forgettable pockets of chemistry that happen to stay liquid a little longer than the rest of the planet. The ice didn't design what came after. It just decided, almost by accident, which lineages got to keep playing. And every time you look up at a blue sky, or a green forest, or your own reflection, you're looking at the winning side of a filter that once came within a few degrees of shutting the whole thing down.